Hello, I am Pranavin Raj from Department of CSC AML. Today I am going to explain about the topic metric representations of graphs, understanding graph theory through matrices. Why use metric representation? It simplifies computation and storage, enables algorithms analysis, pathfinding connectivity, useful in adjacency queries and metric operations. Metric representation of graphs are central to graph theory because they convert graph structures into numeric forms, enabling efficient storage, computation, and analysis through linear algebra. These representations are particularly critical in areas like network analysis, AI, bioinformatics, and spectral graph theory. Core metric representations. The adjacency matrix. The adjacency matrix represented by a square matrix A of G equal to Aij, where Aij equal to 1. If there is an edge between vertices Bi and Bj and 0, otherwise, for weighted graph Aij holds the edge weight. The features of adjacency matrices are time complexity of OI for edge lookup, space complexity making it ideal for dense graph, symmetric in undirected graph, asymmetric for directed ones. These are used in graph transversal, network flow, and spectral analysis. The pros are these. The pros of this adjacency matrix is it is easy to implement, fast edge lookup, but the cons are its space insufficient for sparse graph. Now next graph we are talking about is incidence matrix representation. It is a matrix of Bij of size V cross E, where each row corresponds to a vertex and each volume to an edge. Vij equal to 1. Vertex Vi is incident to edge Ej is 0. Example with a graph and incident matrix. The row represent vertices and column represent edges. The characteristics of this incident matrix is suitable for sparse or structural graph. It captures connectivity without duplicating edges. It is well suited for linear algebraic operations and network modeling. Next matrix we are talking about is Laplacian matrix. The definition is where L equal to D minus A, where D is the degree matrix and A is the adjacency matrix. It is used in spectral graph theory. Applications are clustering, graph partitioning, network analysis. The properties of Laplacian matrix is this encodes its density and connectivity. It is used in algebraic graph theory and spectral clustering. It also used in eigenvalues of indicate connectivity. The number of zero eigenvalues equals the number of connected components. And the next matrix we are talking about is signless Laplacian matrix. It is defined as Q of G equal to D of G plus A of G. It provides a stronger graph characterization and improves eigenvalue based analysis as demonstrated in Stravinsky and spectral studies. The next thing we are going to discuss path, circuit, and cut set matrices. The path matrix it represents all simple paths between nodes important for routing and reachability. The circuit matrix, in which each row corresponds to a fundamental loop, aiding circuit and network analysis. The cut set matrix it identifies group of edges that, when removed, disconnect the graph, critical in reliability and flow optimization models. As you can see here, the comparison of matrix adjacent matrix size for V cross V. This is Space efficiency, fast edge lookup. It's ideal for dense graphs. It is adjacency matrix is very low in space efficiency with direct edge lookup and spectral methods. Incident matrix dimensions from V cross E. This is ideal for sparse graphs. It is moderate in space efficiency. It is used in linear formulations, network modules. Laplacian matrix dimensions of V cross V. It is ideal for analytic modeling, that is it's moderate in space efficiency. It is key used in clustering and eigenvalue analysis. The next is circuit or cut set matrices. It is dimension are just variable. It is ideal for specialized analysis. It is has high space efficiency. It is used in electrical and flow networks. In last we have signless Laplacian matrix dimensions of V into V, that it is used for ideal for eigenvalue optimization. The space efficiency is moderate and it is key uses graph structure characterization. The applications in real life. Applications in real life in social networks, the connection with friends and family, routing algorithm like GPS, internet, maps, Google Maps, image segmentation and computer vision. And also in machine learning, graph-based models. So metric representation are crucial for graph algorithms, BFS, shortest paths, centrality calculation. In machine learning, it is used in graph convolution networks known as GCNs, and is also used in engineering systems, circuit and flow network analysis, spectral graph theory. In eigenvalues, eigenvectors reveal structural patterns and symmetry. These metric frameworks not only simplify computational representation of graphs but also breeds discrete graph problems with continuous linear algebra, unlocking the power of eigenvalues and matrix operations for complex system modeling. The challenges and limitations. If you want to use large graphs, it is you can face the memory issues. The sparse graph is inefficient for adjacency matrices. The dynamic graph is frequently you need to update the dynamic graph frequently. Whenever there is an update, you need to change it very frequently, and there are some limitations regarding these graphs. And next, we want to conclude that matrix representation offers powerful tools for graph analysis. Choice depends on graph type and application. Future directions, quantum graph algorithms, graph neural networks, and choosing the right matrix representation depends on graph density, use cases, storage, constraints, and types of operations needed. For dense graphs or algorithms requiring quick edge checks or adjacency matrices excel. For sparse graphs or those involving algebraic manipulations, incidence or Laplacian matrices suit better. Overall, matrix representation offers powerful tools for graph analysis. The choice depends on graph type and application. Overall, matrix representation converts graphs to forms, enable linear algebra techniques, enabling advanced analysis and algorithm efficiency in diverse fields such as machine learning, network science, and engineering. To understanding the trade-offs of each matrix type ensures effective use and deeper grasp of a graph structure. To summarize these key differences, I am going to conclude with the summary adjacent matrices. The direct connection view optimal for dense graphs and quick edge queries, whereas incidence matrices offer an edge-centric perspective suited for sparse graphs. and detailed generals. The choice depends on graph characteristics and the specific algorithm or analytic needs. I hope you understand this. Thank you.